Is the presentation visible?
Yes, sir.
So last day we have discussed about stationary random processes and ergodic random processes. You must remember one thing. It is very difficult to determine whether a particular random process is ergodic or not. And in many cases, you will come across only a single sample realization of the random process. If that be the case, then how will you understand that whether that sample realization is it belongs to an ergodic random process or not? So when a single sample realization is available, you have no other way but to assume that the random process is ergodic in nature. And then you can try to work with the single sample realization. You can obtain the time average, the time mean, the sample mean, the time autocorrelation function, etc. All right, just 1 minute. ক্লাস নিচ্ছি হ্যাঁ ক্লাস নিচ্ছি ক্লাস নিচ্ছি ক্লাস okay, sorry. Therefore you have no other way but to proceed with the assumption that the random process is ergodic. So you determine the time autocorrelation function, the time average, etc. And consider that those are the values for the ensemble parameters, ensemble average, ensemble autocorrelation function. So only when you devise a particular algorithm to process that random signal based on the assumption that it's a ergodic random process, and when you apply this algorithm, depending on the success of this algorithm, you can understand whether your assumption was correct or not. All right, you have no other way but to assume ergodicity. Now come to the properties of autocorrelation function of wide sense stationary random processes. So I am considering obviously real random processes. Now for a real random process, wide sense stationary random process, real wide sense stationary random process, the autocorrelation function is an even function of the lag parameter. So Rx minus tau will be Rx tau. Proof is quite simple. Rx minus tau. What is Rx tau? Rx tau is the expectation of expectation of the product of xt with xt plus tau. Therefore, Rx minus tau will be the expectation of the product of xt with x t minus tau. Instead of plus tau, you have to write here minus tau. So that's what I have done here. Then how would you proceed? You just replace t minus tau with some other symbol lambda. So t becomes lambda plus tau. Then Rx minus tau, it will become expectation of x lambda plus tau times x lambda. All right. So that is simply Rx tau. So Rx minus tau becomes equal to Rx tau. Second property is that Rx0. What does Rx0 represent? Rx tau is expectation of the product of xt and xt plus tau. In this expression, if you replace tau with 0, you get the mean squared value of the random process xt. So this is actually the normalized average power in the random process. So that is another important feature, that Rx0 is the mean squared value of the random process. All these are based on the assumption that the random process under consideration, it's a wide sense stationary random process. All right. Third property is that magnitude of Rx tau is less than equal to Rx0 for all tau. What does it mean? It means that for all values of tau, the magnitude of Rx tau can never exceed Rx0. You understand? So that is the implication. So that is the implication of this property number 3. As a proof, remember that Rx0 is positive because it's the mean square value. So it has to be positive. Now xt plus minus xt plus tau whole squared is greater than equal to 0. So here, if you blow this up, you get this expression. All right, x squared t plus x squared t plus tau plus minus twice xt plus tau greater than equal to 0. If you take the average, the expectation of both sides, what will you get? First will be the expectation of x squared t. Second will be the expectation of x squared t plus tau. Expectation of x squared t, you know it's Rx0. Because we are considering wide sense stationary random process, that means the second order stationary random process. Therefore, expectation of x squared t plus tau will be expectation of x squared t, same as expectation of x squared t. So, second term also on the left hand side will be Rx0. What will be the third term? Plus minus 2 into expectation of xt into xt plus tau. That is 2 into Rx tau. So, that will be greater than equal to 0. That means minus plus Rx tau, it will be less than equal to Rx0. When Rx tau is positive, it implies that Rx tau will be less than equal to Rx0. When Rx tau is negative, it implies that minus Rx tau that will be less than equal to Rx0, implying that in general the magnitude of Rx tau will be less than equal to Rx0. So this property is proved. Fourth one, I'll not give you the proof, just a statement of the property. If a random process xt is ergodic and it has no periodic component, then if you consider this limiting, this limit as magnitude of tau tends to infinity Rx tau, it tends to mu x squared. All right. So that is the case if xt is ergodic in nature. As a special case, if xt is a zero mean random process, in that case, limit magnitude of tau tending to infinity Rx tau is equal to 0. 4a is xt is an ergodic zero mean random process and has no periodic component. That is also important. And has no periodic component, then limit magnitude of tau tending to infinity Rx tau will be 0. Fifth one is the property of periodicity. If xt has a periodic component, then Rx tau will also have a periodic component with the same time period. All right. Just a simplified proof is given here. If xt is periodic in capital T, then xt, I can write it as x t plus k into capital T for all values of integer capital K. So Rx tau will be expectation of xt into xt plus tau. What will be Rx tau plus kt? Expectation of xt into xt plus tau plus kt. Simply here, instead of tau, I am writing tau plus kt. But expectation x with argument t plus tau plus kt, that will be equal to xt plus tau. Because xt is periodic in capital T. Xt is periodic with a time period capital T. Therefore, Rx tau plus kt, this term, it will be equal to expectation of xt into xt plus tau, that means Rx tau. Hence, Rx tau is periodic in capital T. All right. Therefore, a natural logical conclusion is that if xt has a periodic component, then its autocorrelation function also will have a periodic component having the same frequency or same time period as the original periodic component in xt. The wave shape need not be same. The wave shape need not be same, but the time period and consequently the frequency will be same in both the cases. All right, you write this down. So on the left hand side, the first two terms are Rx0. Property 4. Remember one thing, that because Rx tau is an event function for real random processes, real white sense stationary random processes, therefore it's sufficient to consider Rx tau for only tau greater than 0. Because you know from the symmetry property what will be the nature for Rx tau for tau less than 0. sorry. হয়েছে, have you done it?
Yes, sir.
Now here I have just given one example. Suppose you have a sinusoidal signal embedded in zero mean random noise. The sinusoidal signal is xt, and that zero mean random noise is small n with argument t. So y is, say, yt is equal to xt plus nt. Then what will be the nature of the autocorrelation function of y? Because I am considering that n is a zero mean random process, its autocorrelation function, it will tend to zero as tau tends to infinity. So that's what I have drawn in black. All right. Superimposed on that will be the autocorrelation function of the sinusoidal signal. Say if the signal is a sine omega t plus phi, you have studied in your signals and systems course that if you have a signal, deterministic signal, a sine omega t plus phi, its autocorrelation function will be a square by 2 cosine omega tau. So superimposed on Rn tau will be that a square by 2 cosine omega tau. All right. So ultimately, as t tends to 0, tau tends to infinity, what will happen? Rn tau will tend to 0. What will remain will only be the autocorrelation function of the sine wave. That means Rx tau will only remain. So this is actually, you can think that you have a sine wave, or in, as a matter of fact, any periodic signal embedded in a zero mean random noise. Then if you take the autocorrelation, if you compute the autocorrelation function for this distorted signal, then if you observe the autocorrelogram plot of Rx tau versus tau, that is called the autocorrelogram. So if you have a look at the autocorrelogram for a very large value of tau, then you can just find out that there is a periodic signal, and from that periodic signal you can obtain the time period or the frequency. If that periodic signal in sine wave, there is an extra advantage that uh, from that Rx tau, for very large value of tau, you can also obtain the amplitude, because the amplitude of Rx tau, this will be a square by 2. So you can easily obtain a. Do you understand what I have stated? So you may draw it. But write down what I have stated. Those things are not written down here. If you have done it, I am moving on to the next topic.
Yes, sir.
Now, often we consider a normalized autocorrelation function is defined in this way: rho x tau equal to rx tau divided by rx 0. Because you now know that the magnitude of rx tau can never exceed rx 0, this correlation, I mean the normalized autocorrelation function, it will have values in the range -1 to +1. So magnitude of rho x tau, it can never exceed 1. After that, let us have a look at this random process xt. The details are given in this statement of the problem. Suppose you have a random process xt which consists of three member functions. That means three sample realizations. x1t equal to 1, that means a constant value. x2t is equal to -3, obviously for all values of t, that is yet, and that is another constant value. And x3t is a sinusoidal signal, sine twice pi t. It is stated that each member function means sample realization, occurs with equal probability. If that be the case, you are asked to find out the ensemble average mu xt, the autocorrelation function rxt1 t2. You are also asked to find out whether or not the random process under consideration is white sense stationary, and also whether it is stick sense stationary or not. So this is the problem statement. Write down the problem. It is stated that each member function occurs with equal probability. So this statement is, anyway, write it once more. So at every instant t, we have a random variable that can take on three possible values. One is the value of 1, second one is a value of 3 point minus 3, and the third one is sine twice pi t. So that is, these are the values that the random variable representing the random process can take on at every instant. If that is the case, then how will you obtain the ensemble average mu x t? It will simply be one third. What is one third? The probability of uh, x1 t taking on a value of 1. So one third into 1 plus one third into minus 3. The way in which you find out the uh, expectation of a discrete random variable. All right. One third into minus 3 plus one third into sine twice by t comes out. This is the expression. All right. So this is not the expectation is it depends on the choice of time. All right. Rx t1 t2 is expectation of xt1 into xt2. So this is one third 1 into 1 plus minus 3 into minus 3 plus sine twice by t1 into sine twice by t2. All right. So Rx t1 t2, that is the expression. So this is not White-Sense stationary since the mean is not constant, nor is the autocorrelation function a function of t2 difference t1. It depends on the choice of t1 and t2. Hence, obviously, it is also not strict sense stationary. If a random process is not White-Sense stationary, then because it depends on this choice t1, t2, it's also not strict sense stationary. I've written down the problem statement.
Yes, sir.
Because it's not White-Sense stationary, it will also not be strict sense stationary. Because if it is strict sense stationary, it should be White-Sense stationary. Have you written down?
Yes, sir.
Come to autocorrelation matrices. We have discussed about correlation matrix, all right, random vectors, etc. These are mere extensions of that uh, concept. Suppose a random process is sampled periodically at time intervals delta t. So delta t is the sampling time or sampling period. In DSP, we usually represented uh, delta t by tau. So here, because tau is used, the symbol tau is used to represent something else. We are not using that symbol to represent the sampling period, but it's delta t. So the sampling instants are set T1, T2, T3, T4 in this way up to Tn. That means we have collected capital N number of time samples in this way. T2 is T1 plus delta T, T3 is T1 plus 2 delta T in this way up to Tn. So vector representing the different time samples, this is the vector. Xt1, Xt2, Xt3, Xt4 up to Xtn, each of them is a random variable. So it's a vector of random variable, random vector. All right. Since each sample is a random variable, therefore we can define an n into n autocorrelation matrix that will give you the autocorrelation functions for every pair of random variables in that matrix, in that vector X. Therefore, the autocorrelation matrix SEM stands for autocorrelation matrix. It is the expectation of the product of vector X and the transpose of vector X. So this autocorrelation matrix, it will be the expectation of, I have written down the expression, the elements. Here I have shown the elements of this product. This term is xt1 into xt1, next is xt1 into xt2, like that. All right. So if you take the expectation of each of this element, what will happen? First one will be Rx T1 T1. All right. Then Rx T1 T2, like that. In this way up to Rx Tn Tn here. Now for a white sense stationary random process, Rx Ti Tj, that will depend only on the difference between Ti and Tj. So that we are representing by tau. Therefore, these elements of the autocorrelation matrix, there will be a change. Instead of Rx tau 1, it will be T1 T1, it will become Rx 0. Rx T2 T2, that will also become Rx 0. In this way, Rx Tn Tn, that one also become Rx 0. And these are the other elements. So in this autocorrelation matrix, what can you observe? It's a symmetric matrix. Even in non-stationary case, just try to think that even if the random process is not stationary, there also it will be a symmetric matrix. So I have just recalled what is meant by a symmetric matrix. The entries of a symmetric matrix are symmetric with respect to the main diagonal. So if the entries are written as A equal to small a ij, then small a ij and small a ji, they will be same. Now what is happening due to stationarity? Major diagonal and all diagonals parallel to it have identical element. Just have a look. You will find that the major diagonal and the all other diagonals parallel to them has identical elements. Hmm. This diagonal is also, it consists of Rx n minus 1 delta t, all the elements along this diagonal. Consider a parallel diagonal here. In this parallel diagonal, it's Rx delta t, like that. First, write it down.
Sir, do we have to draw these?
If you wish, you may draw it. If you don't intend to draw it, I am moving on. You will understand easily. Now you have exposure to this topic. You'll have. So these are the instants. You have written it, I think.
Done, sir.
Hmm. We also have, the covariance function, CXTITJ. So it is the correlation of the centered random variables, XTI minus mu I, where mu I is the ensemble average at the instant Ti, times XTJ minus mu J, where mu J is the ensemble average at the instant Tj. So we write that as sigma I sigma j times rho ij. All right. Sigma I is the variance of the random variable representing the random process at the instant t equal to ti. Sigma j is the variance of the random variable representing the random process at t equal to tj. And rho ij, we define rho ij in this way. Rx Tij minus mu I mu j divided by sigma I sigma j. Obviously, rho ij will be 1 for I equal to j. Therefore, you can also have the autocovariance matrix. So the autocovariance matrix is as shown here. CX T1 T1, CX T1 T2, etc. up to CX TN TN. Now, if you just recall this expression for rho xy, it's cxy minus sigma x sigma y. All right. Then you can also replace those elements by these expressions. Instead of Cx T1 T1, you may write C1 sigma 1 squared. Cx T1 T2, you may write sigma 1 sigma 2, rho 1 2, and like that, the other elements. So this diagonal, the main diagonal, that main diagonal consists of the variances of the random variables representing the random process at the instance T1, T2, T3, T4 in this way up to Tn. In a compact form, the expression for this autocovariance matrix is the expectation of the product of the X matrix and the mu X matrix. All right. Times the product of the X matrix transposed and the mu X matrix transposed. Mu X matrix you can understand. I've already considered the mu X matrix when I was discussing about probability in general, probability of random variables prior to the random processes. All right, mu X matrix is this one, that transposed. So this is equal to the autocorrelation matrix minus that product.
Done.
If the random process is White-Stein stationary, these variance values, they will be independent of the choice of the instant. So whatever may be the instant you select, the variance of the random variable representing the random process at that instant, it will be same for all instants. Now this type of matrix is known as a Toeplitz. If you want to know in details the properties of Toeplitz matrices, you may consult any textbook on linear algebra. I am simply considering these matrices, autocorrelation matrix, autocovariance matrix, etc., just because I want to make you initiated to these terms and the properties. Because if you, I mean, in some elective paper or in some special paper, you may require the knowledge of these matrices, the covariance and the correlation matrices, etc. Or even if you go for higher studies in signal processing or in some other area, this correlation and covariance matrices, at least you are initiated to that. I am not going to discuss in details about these matrices, their applications, etc. But just an initiation, as an initiation, I have introduced these things. So let's consider one numerical example. So you are asked to consider a White-Sense stationary random process whose autocorrelation function is Rx tau equal to 10 to the uh, 10 times e to the power minus magnitude of tau plus 9. Let us consider three samples taken at three instants of time, say delta t be equal to 1 second, and therefore, as I have stated, n is equal to 3. So the autocorrelation matrix Rx, the elements will be Rx0, Rx1, Rx2, Rx1, Rx0, Rx1, Rx2, Rx1, Rx0. All right. This is the autocorrelation matrix. Now you have to fill this, I mean, you have to insert the values of all these elements because you have a knowledge of Rx tau. Rx0 will be simply in place of tau, insert 0. So you get 10 plus 9, 19. Similarly, by replacing tau with 1, you will get Rx1. By replacing tau with 2, you will get Rx2. So you get all the elements of this matrix. So that is the autocorrelation matrix. which it I am assuming that this random process is ergodic. So mu x square will be limit magnitude of tau tending to infinity rx tau, that will be 9. So mu x is plus minus 3. All right. So the variance will be equal to Rx0 minus 9, that means 10. Rx0 is 19. The Cx matrix, you can easily find out these elements. These are ones, and the other elements you can easily find out. Row 1 comes out as 0.368. So we require only row 2. This is 0.135. This is therefore the autocovariance matrix. So if I give you the incomplete matrix, some elements missing, you should be able to fill up those voids. If the values of some elements are not given to you, but you are provided with other information from which you can obtain those elements. For example, in this autocovariance matrix, if this particular element, its value was not provided to you, you now know the property of this autocovariance matrix. So you should be able to fill up this void like that. Okay, let's stop here today. So we'll meet on Saturday at 2:30. All right. When you complete, please let me know.
Sir, done.
Okay. So I am just logging out.